In today's video, we're going to look at some of the consequences to the solution of Kepler's problem, which we derived in the previous video. We will arrive at our conclusions only using geometry and trigonometry, without calculus. So first, I'll state the three Kepler's laws. The first one says that in reference to the Sun, the trajectory of each planet is an ellipse. The second law is also called the equal area law. During equal time duration, the area swept out by the planet's focal radius vector is the same. As a result, the planet travels faster when it's closer to the Sun, and travels slower when it is far away from the Sun. And lastly, the third law says the period's orbit squared is proportional to the major axis cubed. These three laws were first discovered empirically by Kepler. What we're going to do in this video is to deduce these three laws using the solutions to Kepler's problem, which we derived from the laws of classical mechanics. And lastly, as a bonus, we will give a convenient method to calculate swept area. The first law was already proved in the previous video, so I will start with the third one. Let's first recall the equations for time evolution. The first equation is called the Kepler's equation. Given t, we can solve for the dimensionless parameter xi. Here, m is the mass of the planet, a is the major axis, and alpha is the proportionality constant in the potential energy, as explained in the previous video. Once we have xi, we can calculate the positions x, y, where the coordinate system is set up as such, as well as the distance r from the star. For convenience, we define m as the time t divided by the constant on the right-hand side of Kepler's equation. This is called mean anomaly in astronomy. So now the Kepler's equation reads m equals to xi minus e times sine of xi. In astronomy, xi is called the eccentric anomaly. Pretty weird names in my opinion. The key to proving the third law is to calculate the period, that is, the time it takes for the planet to complete a full revolution around the Sun. We notice that the pair x and y is 2 pi periodic in xi. From Kepler's equation, when xi is equal to 0, m is 0. When xi is 2 pi, m is 2 pi. When xi goes from 0 to 2 pi, m elapses by exactly one period of the orbit. And since m is proportional to t, we conclude that 2 pi is equal to the period, capital T, divided by the constant. Rearranging it, and we get t squared over a cubed equals to 4 pi squared times m over alpha, which is of course a constant. This proves the third law. Let's continue and prove the second law. In this diagram, we have the upper half of the elliptic path. We're going to construct an auxiliary circle that has radius a, the major axis. The ellipse is tangent to the circle at the two endpoints. We then establish the coordinate system xy as shown. The origin C is at the center of the ellipse and the circle. The Sun is at the focus F. The right endpoint P is the perihelion. And let A be an arbitrary point on the ellipse. Then draw the line segment between AF. We wish to calculate the area of the sector AFP. This is the area swept out as a planet moving from P to A. To that end, we will use the circle. We first draw a vertical line through A, which intersects the circle at A'. Then we draw a line segment between A' and F. The ellipse can be thought of as a result of a vertical compression by a factor of B over A. Here B is the minor axis. Therefore, the area of the elliptic sector AFP is just the area of the circular sector A'FP times the scaling factor. Notice that the area of the sector A'FP is the area of A'CP, area of the triangle A'CF. To calculate these two areas, let's recall A has coordinates A times cosine xi and B sine xi. A' and A have the same x coordinate. By scaling, A' has y coordinate A times sine xi. From this, we can see that the angle A'CP is xi. This gives the eccentric anomaly xi a geometric meaning. So the area of A'CP is just half a squared times xi. And the second area, the area of the triangle A'CF, is half CF times the height. By a property of ellipses, the distance from one of the focus to the center of the ellipse is AE. So we have minus 1/2 AE, the height, which is A times the sine of xi. And we get half A squared times xi minus E times sine of xi. but xi minus e times sine xi is exactly the mean anomaly, M. So at this point, we've shown that the swept area, the area AFP, is proportional to the area A prime FP, which is proportional to the mean anomaly. But as we know, mean anomaly is proportional to time, therefore the swept area is proportional to time. This concludes the proof of the second law. In the last part of this video, let's consider the following problem. We wish to calculate the time it takes for the planet to travel between two arbitrary points A and B. By the second law, to do so, we need to calculate the swept area, i.e. the area of the sector AFB. Of course, in principle, we can do so by integration. But as we said earlier, we wish to avoid calculus, because it turns out that the integral is quite difficult to evaluate. And here is a cool result, known as Lambert's theorem. So the Lambert theorem says that the area of the sector ABF is determined by the three side lengths of the triangle ABF, as well as the axis lengths, little a and little b. By the length of AB, I mean the length of the chord, not the arc. This is particularly convenient for practical calculations in astronomy, because these straight line distances are directly available. We will prove Lambert's theorem and give the formula for the area ABF. Let's start by writing down the coordinates of A and B in terms of their eccentric anomalies. Let xi and xi prime be the eccentric anomalies of A and B respectively. That means A has coordinate little a times cosine of xi, b sine of xi, and the coordinates of B are similarly given. We can write the area ABF as the difference between the area PBF, where P is the perihelion, and the area PAF. By our proof to the second law, the two sectors can be written in terms of their eccentric anomalies. Collecting the terms, we get that the area equals to half AB times xi prime minus xi minus E times the difference between the sine of xi prime and the sine of xi. Now we let phi and phi prime satisfies. Phi prime minus phi equals to xi prime minus xi. And also E times sine xi prime minus sine xi equals to the sine of phi prime minus sine phi. Our goal is to express the variables phi and phi prime in terms of the distances in the statement of Lambert's theorem. To do so, we're going to use some trig identities. We label these two conditions as 1 and 2 respectively. Starting from the second condition, we're going to use a trig identity known as difference to product formula. And this is what the result looks like. Notice that on both sides, the sign factor cancels because of condition 1. This will be useful for us later. Now let's try to express the distance between A and B. Let AB be delta. We can write delta squared as A squared times cosine xi minus cosine xi prime squared plus B squared times sine xi minus sine xi prime squared. We then use the difference to product formula again, and the result looks something like this. Notice that 4 times sine squared term is a common factor. So we get 4 sine squared of xi minus xi prime divided by 2 times A squared sine squared xi plus xi prime divided by 2 plus B squared cosine squared xi plus xi prime divided by 2. B squared can be written as A squared minus A squared times E squared by the property of ellipses. So inside the bracket, A squared times sine squared plus an A squared times cosine squared gives us just A squared. And also by condition 1, xi minus xi prime is just phi minus phi prime. Recall that earlier we have E times the cosine of xi prime plus xi divided by 2 equals to the cosine of phi prime plus phi divided by 2. So finally we have delta squared. So at this point we have delta squared written in terms of phi completely. Taking square roots on both sides, delta is 2a sine of phi prime minus phi over 2 times sine of phi prime plus phi over 2. Use the trig identity once again, and we get delta is a times cosine of phi minus cosine of phi prime. Now let's turn our attention to the distance AF and BF. Notice that these two quantities are already calculated in the solution to the Kepler's problem. Right here, we have the distance r to the star equals to a times 1 minus e times cosine of xi. Let's now add these two expressions together and see what happens. R plus R prime is 2a minus ae cos xi plus cos xi prime. Use the sum to product formula, and we get 2a minus ae times 2 times cosine the sum half and times the cosine the difference half. Recalling our relations earlier, and we get 2a minus 2a times the cosine phi plus phi prime over 2, cosine of phi minus phi prime over 2. And the second term is just a times cos phi plus cos phi prime. So at this point, we have two expressions, one for delta and one for r plus r prime. We can then solve for phi and phi prime from these two. This will accomplish our goal because we were able to write the area of ABF in terms of phi and phi prime. Now that phi and phi prime are about to be expressed in terms of the length AB, AF, BF, and the axis length. And this will prove the Lambert theorem. Adding the two equations together, we notice that the cosine phi cancels, so r plus r prime plus delta is just 2a minus 2a times cosine of phi prime, which we can then use the half angle formula to write as 4a times sine squared of half phi prime. And similarly, r plus r prime minus delta is 4a times sine squared of half phi. Finally, we have the full statement of Lambert's theorem. Given the three side lengths of the triangle ABF, as well as the axis length of the ellipse, we can calculate the area of the elliptic sector ABF. The formula involves the intermediate variables phi and phi prime, which are calculated from those aforementioned distances. And that's the end of today's video. Have a great rest of your day, and I'll see you next time. Bye.